Everybody, what we're going to look at today is this idea of using static equilibrium to solve a couple problems. We're going to do 3 different types of problems with you and see if we can figure out the forces that are involved. In this problem, there's someone holding an object out in their hand, just holding their hand out at a right angle, and the question is, what is the force in that bicep? So how strong does your bicep have to be to just hold a weight far away from your body? The bicep comes down just in front of the elbow, not at the elbow. And the length of your arm is around 30 centimeters. So let's set this up and try to solve for that force. Alright, so here's our setup. We've got the bicep, which is attached towards the elbow joint there. You've got the arm bone, the upper arm bone coming down. The joint is the elbow, that's our pivot point. Then you've got your forearm going out with your hand out holding your physics book. So let's say your physics book is 6 kilograms, seems reasonable. And we want to know how much force your bicep would need to lift that up. So if I analyze forces, we can go down the line and say, okay, the physics book is pulling down. The arm is pulling down as well. The arm has weight to it. And the bicep must be pulling up. Now there's one other thing that's acting on the elbow joint there. Acting on the elbow joint would be this upper arm, and the upper arm is going to be acting either up or down. I'm not really sure which way it's going to go. So I'm going to put a question mark next to the force the elbow joint feels all the way over here. So let's set up our sum of forces. Our sum of forces across, remember, has to add up to 0. We're going to say 0 equals the force in the elbow plus the force in the bicep minus the weight of the arm and minus the weight of the book. And we know that the book is 6 kilograms, so that's going to be an easy calculation for you. Let's say that the mass of an arm, if you lop off an arm, you probably get about 1 kilogram of mass. So we're able to get those 2 forces. The things we don't know is the bicep force and the elbow force. So the question is, how strong are those and which direction are they pulling in? Forces aren't enough. We're always going to have to go to torques to make sure that everything's going to cancel out for us. Again, rule number 2, make sure your torques add up to 0 and pick your pivot point. Since that force in the elbow, we're not really sure which way it's going to point, I'm going to make that my pivot point. It's going to be a little easy to pivot off of the elbow. That way I can go straight out and look at all my torques. So first, I don't need the torque from the elbow. We're going to use the distance from the elbow to the bicep to be a distance we'll call D. And instead of the 3.4, I'm going to use D as 3 centimeters. The whole length of the arm, is going to be 30 centimeters all the way out to your hand. So let's set up those torques. First torque is the bicep. Bicep, if you do your R cross F, you get the thumb pointing out of the page, which is positive torque. So that's the force in the bicep times the distance D, and they're at 90 degrees, so that's nice and easy. The arm itself is going to give you a negative torque if you do your R cross F. So that's the force in the arm multiplied by the distance the arm is from the pivot point, which is half of 30 centimeters, so about 15. And then I'm going to subtract the weight of the book times the distance it is from the pivot, which is the full 30 centimeters out. So again, now that we've done our torques and we look at our torques all the way down the line, things that we have, we know the distance, we know the weight of the arm, the weight of the book, and we know how far they are from the pivots. Go ahead and solve for the force in the bicep. So what you end up getting here is 637.65 newtons of force in the bicep in order to hold that book up. Now, the book itself, or 6 kilograms, which is around 60 newtons, is around 13 pounds. So it's a pretty heavy book. But if you go to the bicep is requiring about 140 pounds to pull straight up to hold that 13-pound book out. Why does the bicep need to be that strong? Well, the bicep is attached very, very close to the pivot point. So because of that very, very small distance, it requires a very large force to hold a small force, which is the book, out at a very, very long distance from the pivot. Just know it looks like your bicep is a very inefficient lever in trying to hold things up. Now that we've got the force in the bicep, go back to your force equation and substitute all your numbers in. And when you do that, you find that the force in the elbow ends up being negative 568.9. So that means that the force in the elbow is, or just a little bit less than the bicep, but now we know a direction. The force in the elbow must be pointing down. So the upper arm pushes down on the elbow joint based on summing my forces all the way across the arm here. So let's move on to the next one. Next one is a sign. So looking at the sign here, we want to hold a sign far away from the wall, and the question is, how much tension do you need in your cord? The cord is attached to the far end, and I'm going to move that sign in a little bit and not put it at the far end. I'm going to try and take some of that weight off of the cord. So let's set this up and show how we're going to balance our forces now when you've got forces at angles. Alright, so here's our setup. We've got a wall to the left, we've got a bar that goes straight out. Off the bar I'm hanging my sign for the restaurant, and off at an angle is this tension in the cord. So the question is, what is that tension in order to hold my sign up? Let's give you some values here. The length of the rod is going to be 2 meters. The mass of the rod is about 25 kilograms, so a pretty hefty rod. The sign itself has a mass of around 100 kilograms, and the angle that this makes with the wall is around 40 degrees from the horizontal. So those are the things that are given to you. The question is, how much tension does that cord actually take? So let's go again and identify forces. First thing I'm going to do is the force of gravity of the sign. The weight of the sign is pulling straight down. The bar is being pulled down by gravity as well, right around its center of gravity. The cord is pulling right along the rope here at an angle. And so if I just look at that, that means that I've got tension that goes upwards to counteract the down forces, and I've got tension that goes to the left. So if I know anything from my sum of forces and sum of torques, I know that all my forces have to cancel out and all my torques must. Right now I see that I have a left force. That means I need a right force. So where am I going to get this right force from? Well, go over to the wall and look at the hinge. The hinge must be pushing to the right, and possibly pushing up or down. Not 100% sure, kind of like we did with the elbow before. So I'm going to put the force right there. Right now up. If it's not up, we'll erase it and draw it down for it actually being negative. So that's my forces. There's a force in the wall over here. There's a force from the cable, and there's the two gravitational forces down. You're now going to have to look at forces in all directions. So we're going to have to sum forces in the x direction, and we're going to have to sum forces in the y direction. So when we sum forces, no matter which direction we pick, they must add up to 0 for things to be in equilibrium. So let's go with our x forces. I see there's tension in the x. So I'm going to say, okay, tension in the x is negative. And I'm going to have to add that to the force from force of gravity of the sign, which is down, minus the force of gravity of the bar, which is down, plus the tension in the y direction. And there's one other force we're going to add in. I'm not sure which direction it is, but we'll call it the force of the wall in the y direction, or force of Wally. So now we've got all our forces set up here. So knowing those two forces, I've got two of my things. Looking at my x direction, I can see there's only two forces, and they're equal and opposite. That means that if I can find tension in the x direction, tension in the x will equal whatever wall x equals. So that's kind of nice, but I don't know either one of those. So let's look at the y direction. I still don't know the tension in the y, and I don't know the force from the wall in the Y direction either. So if we're out of options with force, we've got to go to torque. Okay, when summing our torques, we got to make sure all our torques add up to 0. And looking back here, we've got angled forces on both ends of the rod. I'm going to pick the pivot to be right here. That way we pivot and I don't have to worry about that wall X or wall Y. I can just worry about the angled forces all the way out. So let's go down the line and see the first torque you run into is the bar. So the bar is acting at half of the length of the rod. The sine is acting at 1.5 meters from the end point. And the rope is acting all the way at the full 2 meter mark. But remember, for torques, I only care about one component of the force. I only care about the perpendicular component. So you can focus on the TY here, but be careful with your angles. You're going to have to use cosine of 50 degrees, or you could use sine of 40 degrees, depending on which way you write that out. So let's write out our torques. So the force of gravity of the bar times 1 meter, that's half the length of the bar, is in the negative direction for torque. Also, we've got a negative force of gravity of the sine times 1.5 meters. If you look at the rope is torquing in the positive direction, so that's tension sine of 40 degrees, because remember I need the perpendicular component, and that's all the way out at the 2 meter mark. So now you've got your numbers, you should be able to solve for tension. That'll get you the full on tension, and doing all your work, you'll end up with 1,335 newtons. So that is the full tension in the rope. Not the X tension, not the Y tension, it's giving you the full tension since I wrote it out in that form. So that helps me. That says that, okay, I've got the full tension in the rope, which is probably the ultimate goal, but I need to break that into its components. The 1,335 is the hypotenuse, so you got to use your trig to figure out what Tx and Ty are. (1,023 newtons), and you look for Ty to be around 858 newtons. Plugging in some of those values if you want to go along the way. If I know Tx, that means I now know what the wall X is. The wall X must be pushing to the right at 1,023 newtons. I now know Ty, so that now I can use my work to find the force from the wall in the Y direction. And the force from the wall in the Y direction ends up being around 367.8 newtons. So we've got forces all over the place here. We now know the full tension in the rope is this, and we know that the hinge acting on the wall is being forced to the right to hold the bar off the wall, and it's actually pulling up to help that bar from slipping down and sliding down. So if you think about it, the hinge is actually applying a force, a net force, off in this direction. One thing they may ask is, what is the real force in the hinge? They're asking about the hypotenuse, not the two components. So I'm glad you got the two components, but we want to know what the full force in the wall is. So doing your work, you get around 1,087 newtons. And the question would be, well, what angle does that force act at? You have to do some trig and end up around 70 degrees. So the hinge is pushing off away from the wall, and the rope is pulling into the wall. So you could go at this a couple different ways and think about what happens when things fail. If the hinge fails, the two torques from the sine and the bar's weight makes the whole thing rotate counterclockwise. If the rope fails and the rope disappears, now the two weights and the torques cause clockwise rotation, and the sine swings down and into the restaurant. So that bar does not want to stay there. It is staying there due to the forces and the torques canceling out, but if one of those forces disappear, and you will have angular acceleration or linear acceleration. And we kind of did this today in class. Let's talk about the ladder. So we've got a ladder. sitting here and someone's climbing up the ladder. Okay, so like we talked about today, we've got the person climbing up the ladder, and we want to know the forces that this ladder does feel. Well, first thing we know is that there is a force of gravity from the ladder pulling down at its own center of gravity. The person has its own force of gravity pulling straight down as well. So there's two down forces. It means we need an up force. Well, the up force is going to come from the ground supporting the ladder. So I've got a normal force from the ground pulling straight up. Alright, while the wall, or the ladder is leaning against the wall is going to push back and support the ladder off to the left. Well, if we want to balance forces, if you look at everything right now, I can see that there's an unbalance in the X direction. That means the ground is going to have to push to the right to cancel out that leftward force. So let's name what these forces are. This obviously is the force of gravity of the person. This is the force of gravity of the ladder. This would be the normal force, or the support of the wall. Over here, this is the normal force of the ground. And down here, we've got the force of friction helping you not slip and slide off the wall. Let's balance our forces and balance our torques. Negative force from the wall plus the force of friction. Ta-da! Done there. The weight of the ladder minus the weight of the person plus the normal force from the ground. So giving you some values here, let's say that the ladder has a weight of 150 newtons and the person has a weight of around 700 newtons. So we actually do know our vertical forces. We know the ladder weight and the person weight. So we actually already know what the ground's doing. The ground is pushing back up 850 newtons. So that was easy. We actually got one of those without even having to look at torques. But let's look at the force from the wall and the force of friction. We know those two are equal and opposite because those are the only X forces, but I don't know either one of those. So like we did today, we pick a pivot point and we go from it to solve and make my torques equal 0. I see two forces acting at the ground and one force acting at the top. So for me, I'm going to pick that to be my pivot again. It looks like I'm going to be able to eliminate two torques instead of one torque, and that's what I'm going to go with. So as I go up the bar, I'm going to have torque from the ladder, negative. I'm also going to have torque from the person, negative. And I'm going to have positive torque from the wall. So let's do this. Well, that's just radius times force, but here's the problem with the ladder. Since it's at an angle, and the angle here is 75 degrees, what we need is just the perpendicular component of force to the ladder. So I can break this into two pieces here, and I can break this force. And if I look at my support force in the wall, my support force also can be broken into two pieces. All I want to focus on is these perpendicular pieces. Now you can draw components however you want, just be careful about what angle you're going to use in your math. For me, if the angle down at the bottom is 75 degrees, I can do some trigonometry or geometry and figure out that this angle is also 75 degrees. So is this inside angle, and so is this angle. So those are all 75 degrees. They all look like I'm going to use the cosine component for my weights, and I'm going to use the sine component for the wall. So write them out carefully so that you can solve for these in the end. So let's write out our full torque equation. Alright, so one thing I forgot to mention here was that the ladder was 6 meters long. So the weight of the ladder acts at the 3 meter mark, and that's torquing it in the negative direction. Cosine of 75 degrees. That person is almost to the top of the ladder, so I'm going to say they're 5 meters from the pivot. And then the wall is going to do a positive torque, so that's the normal force from the wall times the sine of 75 degrees, and that's acting at the full 6 meter mark. So again, in terms of forces, you know the weight of the ladder, you know the weight of the person. Using the torques here allows you to solve for the weight or the force in the wall, and that force in the wall will help me find the force of friction, about 176.4 newtons. So I know how much the wall is pushing. The wall is pushing back the same as the friction force pulling forward. Now something that you might be asked is, well, what is the coefficient of friction? how rough must that surface be so that you don't slip out. And remember, friction is fun. So since I just got the force in the wall, I know the force in the wall is friction. The normal force, going back to here, is 850 newtons, because that was the weight of the two downward forces combined. So that gives me a normal force as well. So I can easily solve for the mu. The mu ends up being about 0.207 for the coefficient of static friction. Why do I want a kinetic friction? Because if it's kinetic friction, that means my ladder's slipping. And I don't want to be on a ladder that is slipping off the wall while I'm trying to hang my Christmas lights.